We're dealing with section 4.5, integration by substitution. And in the first video, I talked about indefinite integrals and basically how we can use u-substitution to simplify a more complex problem into a simpler one that we can deal with and find the antiderivative. We did that. We looked for patterns that we can use with the general power rule and also with just generally recognizing that pattern of f of g of x times g prime of x dx. The second part, I'm going to start playing a little bit more with definite integrals and substitution. So let us move forward onto that. So we go down to... We finished with those, so we'll get into definite integrals. Basically, the big difference between the indefinite and the definite when we're working on it is those limits of integration, that a to b. One thing we can always do is you need to find the base, you're finding the antiderivative. You can go ahead, do your u-substitution, find the integral the way we were doing it in the last video, and then take that back to your original limits of integration, plug them in, and work with it that way. However, we can make it a little easier by if we're doing this substituting, we found the integral, then we substituted u back to x again to apply the limits. Well, if we just change the limits to u, we don't have to worry about x ever again once we got it all switched over to that u substitution. So let's kind of see what that means. So what the theorem states is we're doing the definite integral now from a to b of f of g of x times g prime dx. We make that fu du, and now we change these to g of a and g of b. So what we've done is rewritten these limits of the limits of integration from being in terms of x to being in terms of our new function g of x. So let's do this example. We're looking at the integral from 2 to 5 of x times x squared minus 3 quantity squared dx. Whoops, hit the wrong button. And so we do our substitution. We say, well, if we let u be x squared minus 3, then du is 2x dx. And you notice here, I didn't stay solving for dx. I have x dx is what's left over. So x dx is just du over 2. But then now I say u is x squared minus 3. So if x is 2, u is 2 squared minus 3 is 1. At 5 squared minus 3 is 22. So now I can rewrite this interval totally in terms of u. My limited integrations are in terms of u, 1 to 22. I took the 1/2 out, and I'm just looking at u squared du. And that's simply u cubed over 3, and I can just evaluate that from those limits of 1 to 22 instead of having to switch it back to x squared minus 3 and plug in 2 and 5. And that's kind of a nice little shortcut. If you really want to, you can go through the other way, but this saves you quite a bit of time. So see if you can do it with these two. I'll give you a minute here to try, and then I will come and see what I got. Yes, I know we're in part 2, aren't we, Daisy? So we look at this first one, and we're going to let u be 2x to the 4th plus 1. So du is going to be 4 times 2 is 8x cubed dx. And so since we have the x cubed and the dx here, I'm going to say du over 8 equals x cubed dx. Now, I'm going to take my limits of integration here. And I'm going to say if x equals 0, u is 2 times 0 to the 4th plus 1 is 1. And x equals 1, u is 2 times 1 to the 4th plus 1. That's going to be 3. So now I can do all of my substitution. So this is u. My integral is going from 1 to 3. 2x to the 4th plus 1 is u to the 2nd power. X cubed dx is du over 8. So I can pull out my constant. And I have the integral from 1 to 3 of u squared du. So that is 1/8 times u cubed over 3 integrated from 1 to 3. So we got 3 cubed over 3 minus 1 cubed over 3 is, why is this a 3 here? That's an 8th. We have 1/8 times, what do we got? 27 minus 1 over 3 is 26 over 24. And that's approximately 1.083. Or you can make that 13/12 if you want. That is that u-substitution. And again, we could have written this back into, at this point, saying, oh, this is 2x to the 4th plus 1 squared cubed over 3. And then evaluate that from 0 to 1. This is much easier. Let's try the second one. You want to try this again on your own, pause the video, come back, see what we got. I'm going to say u is 1 plus 2x squared. So du is going to be 4x dx. And here's my x dx. So I'm going to have x dx is going to be du over 4. I'm going to come along with my limits of integration. So at 0, I have 1 plus 2 times 0 squared is 1. At 2, I have 1 plus 2 times 2 squared. 4, 8, 9 is 9. So my integral is going to go from 1 to 9. This is my u. So I'm going to have u to the negative 1/2 to make it easier to do my integration. And my x dx is du over 4. Or 1/4 the integral from 1 to 9 of u to the negative 1/2 du. Again, this is a simple power. Bye-bye, mouse. So we're going to say that's going to be plus 1 to negative 1/2 is u to the 1/2 over 1/2. So, and we're evaluating from 1 to 9, or 1/4 times 2 square root of u from 1 to 9. So 1/4 of 2 times the square root of 9 minus 2 times the square root of 1. Square root of 9 is 3 times 2 is 6 minus 2 is going to be 1/4 of 4 is going to just be 1. So either way you do it, you can do it the long way around. It's kind of easier since again, it's kind of like when we're doing the definite integrals with antiderivatives, we didn't have to worry about the families. We could just throw out the constant. It's just a little bit, we got to do that with the indefinite integrals. We need to keep track of that. But in the definite integrals, things simplify out. Same thing with this u substitution. If you get everything switched over in terms of u, and you're just trying to get a number, not a function, then get everything switched over in times of u, and you don't have to go back to the x. And it can maybe save you a step or two. Last thing we're going to hit is even and odd functions. And basically these are, again, we're dealing with definite integrals when we're doing this. But remember, if it's an even function, whoops, let's go back. Clear out all of that wonderful work. If it's an even function, f of negative x equals f of x. Even function is symmetrical within the x-axis. So maybe just draw this with an example of an even function here. This side is exactly equal to this side. So if we're going a, negative a, this area and this area have to be the same because it's symmetrical. It's even. So in which case, instead of going from a negative a to a positive a, you can just go from 0 to a and double it because of symmetry. That's all this function says. If it's an odd function, then f of negative a equals the opposite of f of a, or you have this type of symmetry where all of these are opposites of this. Well, we're going from a to negative a. Again, this area is going to be the same as this area, but this one is positive and this one is negative, and they're going to cancel out. So that's, if we know you have an odd function and you're going from negative a to a, your integral will always be 0. If it's an even function and you're going from, again, a negative a to a, you can just go from 0 to a and double it. So those are shortcuts that you can sometimes use. So just kind of throwing those in as a, oh, by the way. But go ahead and work on these problems.